25 minutes, I will talk a little bit about how I use Factsage, CNRS, and SIMaP for building materials. So when I reread my abstracts, I thought afterwards it was very, very specific and more destinated to building material people. So my talk will be much broader than what I put in the abstract. Okay, I will start with a few slides on building materials as a whole. And then I will concentrate on the cement clinker mineralogy prediction, because that's the name of the game in cement-related research at high temperature. I will spend most of the time on ordinary Portland cements, OPC, which is the standard cement. 99% of the cements that you can buy is OPC. But then I will give you one or two slides on low CO2 clinkers. Not so much, because in the second talk of this session, there will somebody talk about carbonatable clinkers, and so I didn't want to go much more into detail. And then at the end, I will talk a little bit about kiln SIMaP again. Shiva will talk about it at the end, and Cassie at the end of the talk. So I will just give you a few slides on how I use kiln SIMaP in my research. And one final slide on hydration, because there is not only high temperature thermodynamics, but also aqueous thermodynamics that you can do with building materials. Okay, just a few key messages. Concrete is the second most manufactured material by mankind after water. And annually, 7 cubic kilometers are poured into the nature to build houses, bridges, or whatever. And the materials that we have are aggregates, which are the stone, sand, water, and cement. And in that list, the only one really made by a high temperature process is the cement. All the others, the aggregates and the sand, are manufactured. They're treated, but not in a high temperature process. So the produced quantity of concrete is twice as much of all other materials, just as a rule of thumb. You take steel, aluminium, whatever, and you multiply it by 2, then you get the concrete. Just to give it a flavor how much is lying around, and which made building materials important, not by itself, but just by the sheer quantity that you have lying around. And the world production for cement in 2024 was 4 gigatons, which is already down by 10% compared to 5 years ago. So the production is declining because most of the developed countries have built whatever they needed, and it's more or less, and even China also starts to go down. So it's just a few continents and countries are still producing a lot, like India. India is on the upstream, but all the others basically on the downstream. And just to give you a few numbers, for the thermal energy you need is 1.8 exajoule, which is 10 to the 18th joule. The electrical energy for just producing the cement is 300 terawatt hours, which is the annual consumption of a country like the UK or Italy. And the dark point is the CO2 emissions. For roughly 1 ton of cement, you have a half a ton of CO2 going into the atmosphere. Okay, just a little bit of terminology. Cement is the gray powder that you see here at the end. You can either buy it in bags, or you can buy it or if it's a big building, it's shipped by trucks. When you mix it with water, you call it paste, and that's what we do in the lab, in order to characterize different cements or different the reactivity of different powders. We make pastes and measure on the paste. If you put sand into it, you get a mortar, and if you put aggregates or stones, you get the concrete. Okay. Yes. Good. So, how do you make cement? You start with natural stones. Start from limestone, clay, and some minor additives like iron oxide or calcium sulfate. And then you burn it in a rotary kiln to make clinker. And then this clinker that you burn in a rotary kiln, you add gypsum and other additives, you grind it down to make the final cement. And here in this talk, I will focus on this part, which is the high temperature part, because there is where all the chemistry goes on in the process. As I said before, 8 to 10% of the CO2 emissions worldwide, globally, industrial CO2 emissions, are due to cement production. this CO2 comes 40% from the fuel and 60% from the calcination of the limestone. And in the end, you end up with something which looks like this, which is small nodules. Why they are nodules? Because it's a rotary kiln. Due to the rotary movement, you get some nodules. Okay. When you look a little bit closer on these nodules, so macroscopically they look like this. But when you cut them in half, you polish them, you look on the polished section here. In real life, they're not blue. They're attacked by an agent in order to reveal the phases. The blue one is the calcium calcium silicate, which is also called naturally hydrorite or halite in the cement. Lanite, C2SiO4, are these potato-like shapes here, these gray ones. And then the white one used to be a liquid phase, and upon cooling you get calcium aluminate, calcium alumina-ferrite, which is called brown millerite, and sometimes you get calcium oxide and magnesium oxide. So this is a typical microstructure of a cement clinker. In the old times, people used to do a lot of microscopy in order to check how the burning process worked. Nowadays, it's almost gone, unfortunately. So, but still, we want to know, when I put something in, what is coming out? So the input is the natural stones, as I said, and the natural stones, you can measure the chemical composition. In the old times by wet chemistry, nowadays by X-ray fluorescence. And so you get the basic oxides, but what you want to know is the mineralogical composition. You want to know your amount of halite, which is tricalcium silicate with minor elements, B-lite, etc., etc. So how can we pass from there to there? Experimentally, we have X-ray fluorescence. All cement plants are equipped with XRF measurement systems because it's the name of the game. You have to know what you put in the kiln. But not all of them have XRD equipment. So in most of the European plants, they have XRD equipment with Rietveld analysis, Bruker or Panalytical. And like this, you can make the link from the chemical composition to the mineralogical composition. But you also want to do it theoretically. And already more than 100 years ago, or almost 100 years ago, Bogue used the phase diagrams. Here is a part of a phase diagram and some geometrical rules in order to link the four main components, lime, alumina, iron oxide, and silica, to the four main components in the clinker. So you have four components, very nice. You can make a linear combination of the four. It also works because the solubilities, the mutual solubilities are small. If it would have been big, it would not work. And that's somehow already a little bit the drawback, one of the drawbacks. You see here the C4AF. He's taken as stoichiometric, but in real life it's not stoichiometric. It has some solubility of alumina and iron replacement. So that's one of the drawbacks. But overall, it works fine. And for that reason, these Bogue equations, there are still plants who still use them because nothing better on the market. But then thermodynamics comes into the game. And the first one who published a paper on that was Tom Barry with Fred Glasser from Aberdeen. They used the empty data database for the four-component system and said, let's test our database that we developed for something completely different in the cement system. And surprisingly, it worked fine. Well, surprisingly, they did a good job. And for that reason, it worked fine. So they could calculate, typically, for example, the liquid phase occurs at 38 degrees Celsius, and they could reproduce this low eutectic, etc., etc. So that was the first paper on Kalfa time thermodynamics for cement. And then a little bit later, Högfors and Rainer Backman, they did it in Sweden. They used the Factsage database and calculated also for the four-component system. For example, here, the phase amount as a function of temperature. But unfortunately, they're limited to four components, and the real system is much more complicated. So I chose a different way. I said, let's be pragmatic and make a two-step simulation. The first step is what is going on in the rotary kiln. So my input is the chemical composition that I measure, and then I said, okay, I have here close to the flame, or just below the flame, I'm close to the thermodynamic equilibrium. So let's make an equilibrium calculation at that temperature. The main problem is the temperature is not well defined. You cannot really measure it precisely because you have a lot of dust in the kiln. So I said, okay, I fix the amount of liquid phase and do a target calculation. And that's the way I did the simulation. I fixed it to 25%. And from experience, this is roughly the value, is 25 plus minus 5. And then I do a target calculation to get this maximum temperature, which I call Tmax. And then on cooling, when it falls into the cooler, and here you see how a cooler works. So the nodules fall onto a grate, and air is blown through this to the nodules in order to cool them down. This has two reasons. First of all, you want to cool them down quickly to fix the most reactive phase. And also you want to recover the hot air into the process to make your process more efficient. And so here it's clear it's not an equilibrium cooling. When you blow hot air, a cold air through to the hot clinkers, it's a non-equilibrium cooling, and luckily the Scheil-Gulliver model works pretty fine here. The Scheil-Gulliver that you use, most of you use for metals, also works pretty fine here. So you can all the precipitated solids you can take out of the calculation, and only the liquid phase you go down to lower temperature, and it works fine. Okay, so here's the model. Input is the composition from the XRF measurement. I calculate the high temperature step, which is an equilibrium step. I fix the liquid, I calculate the maximum temperature, and then the cooling step, in which all other phases come out. Oxides, for example, belai, aluminides, etc., but also the salt liquid, because I already have sulfates in the system. So I have then the mineralogical composition that I can compare to real measurements. So just to give you a flavor how complicated the system is, when you start from natural raw materials, you have limestone, you have clays, you have various carbonates. So your system, the full system is here sketched out. And it's clear that I didn't develop a full database for that. So I started with FD oxide. And what I represent here is done with FD oxide. Now we slowly switch over to GTOX. But for the moment, all the results I've shown is a modified version of of FTOX, sorry. And you see, I try to introduce the minor elements into the structure. So we analyze the literature, and we have seen, for example, alumina replaces silica, iron can replace silica and halide, magnesium clearly replaces calcium. I wrote it down here as a sub-lattice model, but it's not at all like that in the database. It's too complicated. I did end members, so full substitution, and then just regular solutions or sub-regular solutions. So it's a very, I would call it engineering approach to the database in order to get a first set of data. And then how do I fixed it? We had a lot of data from point countings. At that time, it was only internal data from Lafarge, where I worked 10 years. Now we publish quite a lot of these data. So anybody who wants to do this kind of job can do it. The data is there now and public. So I have now a database in which I use the liquid phase from FTOX. I use mainly the liquid phase, and then all other phases are coming from their own work, in which I optimize the parameters. And it works pretty fine because the solubilities are small. That's the key to the system. The solubilities do not alter much the phase equilibria, just the little amount needed to get a better fit that you need. Okay. First comparison is halide, so the 3 calcium silicide measured versus calculated, and you see that the line, they're all pretty close to the line. And the mean absolute variation is 2.9%, which is close to the experimental uncertainty of the Rietveld method. One key point here is the quality of the XRF data. We use XRF data as an input, and you see 0.1%, so 1,000 ppm uncertainty on silica gives you already almost 1% in the halide prediction. So part of this difference here may not lie in the model, but may lie just in the underlying chemical composition data. And you should always keep that in mind if you use these kind of data. Be aware that probably your underlying chemical composition is not good enough to, or be assured that the chemical composition is good enough. 1500 ppm in lime also gives you 0.5% in halide. And if you neglect minor elements, in some plants they do not measure sodium, potassium, sulfur, phosphorus, and titanium, can give you an uncertainty of plus minus 1.5. So you really need to take into account all of them. Some interesting feature is, as I said, you indirectly calculate the liquidus temperature, where you have 25%, and this is a comparison of measured data compared to the calculated. And if you see probably plus minus 50 degrees, you're always in the uncertainty. So that's also a good indicator that your model is not so bad. And you can also, and this is the advantage, you can calculate specific heat consumption. So you start with limestone, alumina, clay, whatever you choose as a raw material, and you calculate the full heat balance for making the clinker. And here this is given lime saturation factor is basically a constant calcium carbonate. And you see even for a constant calcium carbonate, you have a variation of plus minus almost 10%, plus minus 5%. And if you know that a company pays a few billions of euros or dollars per year in fuels, even 5% may be an interesting value for them in order to optimize. So that's the power and the advantage of using a thermodynamic approach. But here the interesting thing is, it's not obvious to see which are the parameters that govern this specific heat consumption. You cannot just draw a linear line, makes no sense. So there, my idea is to calculate a lot of data points and do some machine learning, basically running AI methods over it in order to detect the parameters that are really behind these specific heat consumption of a clinker. We can measure some stuff, and these are some drop results. And this is the heat of cooling, because the clinker, once it is formed, we have all the data. We have the high temperature data, we have the room temperature data, so we can calculate the heat content, and we can measure it. And you see that that was an indirect test, that the modeling was not too bad, because except this one and this one, all of them were in way in between uncertainty. Alternative raw materials is a big thing now. When we don't want to use limestone or other stuff, and we have so many slags lying around, can we use some of the slags? The advantage would be no calcination if it's lime-containing slags. So less clinkering heat, less calcium carbonate, less CO2. So overall we win. But the problem is slags are very hard to grind. So you would need electrical energy in order to prepare them. You run into kinetic problems that when you start with these slags, the reaction kinetics may be slower. And most of the time you have unwanted minor elements, for example, chromium oxide. Nobody wants chromium oxide because even at 1500, you have calcium chromate, which is Chrome 6, very, very stable. So therefore, chrome oxide is, or vanadium oxide. Vanadium oxide has also a problem that has a low melting point and attacks the refractories in the kiln. But let's assume it works out fine. If you replace 10% of the calcium from the slag, from the limestone from the slag, you already win almost 9% theoretically, which means 4.5% if you take into account heat losses in the process. So again, interesting, but needs further study. So clinker summary, just full clinker cement quality loop can now be established. You have experimental data, you have theoretical data, you can compare. So you can check the integrity of your measurement system, you can set targets, you can put up performance models, etc. So with this model now, everything is possible. And as I said, you can evaluate the impact of raw material changes, burning behavior, specific heat consumption, for example. One slide on alternative low CO2 clinkers. We have a whole group which are called BYF, BCSIF, CSA clinkers. Here they are based on calcium sulfur aluminate. Reduction of 20 to 30% of the specific heat consumption, the CO2 emissions and grinding energy. I have a student working at the moment on that, evaluating GTOX, which works very fine for this kind of clinkers. So that's something as a teaser I will report on next year at the user meeting. But it's really very, very good. Then we have these carbonatable clinkers, which the next speaker will talk about. So they are both based on wollastonite or enkenite or amorphous slags. If they are on wollastonite or enkenite, they can be produced in normal cement kilns. And then the little more exotic are magnesium-based clinkers, where they use magnesium mining waste. That is, people in Finland work on that. They extract the magnesium from the mining waste and carbonate, hydroxide them in order to make them also as potential binders. Kiln CMU, just a few slides. So for the cement process, we have the full model. We use the rotary kiln model, but Kari also programmed then the cyclones, the preheater tower with the 4 cyclones, a calciner, and the cooler. So we have all bricks to put together the cement process. We have the full thermodynamics, where we can use stoichiometric compound solution phases, complex gas phase. We can add the kinetics to it. And I still use the Excel interface. So you probably will show the other interface later, but I'm happy with the Excel interface. So the kiln is cut into slices. I won't go into detail because I'm pretty sure you talk about that later. For the cement process, what do we put in? We put in the feed, the kiln feed. That means the raw mix. We can put all kind of fails air, so holes in the system. We put the fuels here, and we put the air here. So basically, we have every input flows that we need, and the output flows then are the gas coming from the stack here. So the gas composition, the gas flow rates, and the temperatures, and that is measured. So the composition and the temperatures are measured, so you really can compare them to real measurements. You can compare also the clinker that's coming out, the chemistry. You have some air temperatures in here, so you have a series of measuring points to which you can compare your simulation. But the good thing is you can have other what I call soft sensors, where you have data points from the simulation, for example, in the mid-kiln or somewhere in the cyclones, that you cannot really measure, but may be important in the process. So we used it for one example where we used 30% of oxygen. So we enriched the flame with oxygen, and we wanted to know how the temperature changes and every other parameters the same. And you see the dotted line is the modified temperature, so it becomes a little bit sharper than before. And what you also can calculate to trace then, the simulate is all the species. For example, here, which is interesting, you still have limestone far into the kiln. And that makes sense, because here the temperature is pretty low. Oops, sorry. The temperature stays rather low until, let's say, here, until 80 meters into the kiln. And that is, what a surprise, where the limestone disappears. So the limestone somehow acts as a heat sink for the full system. And then you see all the phases that forms, the C3S that we want, the C2S. But here, if you would not put any kinetics into the system, it would form immediately. And that's the thing. So that's something you should adapt. And so it's not, when you use kiln CMU for cement, it's not just you put everything in, you say start, and you get the result. You have to adjust the kinetics, you have to adjust to real measurements in order to get a reliable model afterwards. So it takes time. Just one slide on a very experimental kiln in Poland, in Nowa Huta, close to Krakow. You see it's a 7-meter long kiln with a bigger section in the middle. And so we calculated the profile and we measured 1350. And here the measurement is reliable because we don't have any dust, and we calculated 3070. So the agreement is very, very good between the simulated and the measured temperature profile. One slide, as I said, on cement hydration. In principle, everything can be done with Factsage. The problem is the database, and then we need a lot of hydrates, like ettringite, like garnets, etc. So this data is there, but it's not really in our databases. So that's something, for example, as SGTE, I should work on to put these into the database so that we can use. Then you can calculate phase diagrams. This is typically the type of phase diagrams that they calculate with the concentrations of alumina ions, silica ions, and calcium ions in solution. Klaus, a few years ago, has shown a different way of showing these aqueous diagrams. Basically, they're equivalent. It's just a question of flavor. And then what they do is they want to use to know the space filling with the phases. So therefore, you would need molar volumes of the phases in order to see the thermodynamic equilibrium gives you an amount, and you have to transform it into phase, because when it comes to concrete, the name of the game is space filling. The more you fill the space, the harder is the concrete. It's as easy as such. The less voids you have, the better. Okay, conclusions, outlook. So thermodynamic simulations are really a valuable tool in clinker research. And I forgot to say that the model I've calculated with ChemUp, because at that time there was no process flow or fact flow or something like that. So I had to program it in ChemUp. I've shown you the old version. There's a new model that we are currently developing in the frame of a European network. My PhD student, Ramon Bandag, is doing that. So probably in a year, we will publish everything, and like that, everybody could use the model having Factsage. It will not be a standalone database. It will be the add-on to Factsage, which is good news for the GTT, because people want to use it, have to buy a license. As I said, the new alternative low CO2 clinkers works fine, especially the ones based on calcium sulfur aluminate. Carbonated clinkers in cement. There is also another European network looking on carbonation, which is called Contrabas. Also some part of thermodynamics going in there. And process simulations to tackle operational problems. Evaluate the production capability of new clinkers. This is in the case of these low alternative clinkers, but also performances of the actual process in terms of volatilization or build-ups and ring formation, as I discussed before. Thank you.